I'm so thrilled to have such a great crowd here tonight. My name's Ken Goldberg, and I have the good fortune to be the chair of the Faculty Advisory Board, representing the faculty of this fine institution. So it's a pleasure for me to welcome you. I'm really sorry I didn't wear my Berkeley t-shirt tonight. Actually, I know it's terrible. So I just ordered a second one that I'm going to keep in my office for such situations. And it's only in Berkeley can we get a great turnout on a super hot night in the middle of the summer to celebrate the atomic elements. Um, and I want to say thanks to you for coming. Jacqueline McCormick is here from the Berkeley Mayor's Office. Rena is our director. She and Susie Gregory are responsible for organizing this wonderful institution, and all of the wonderful staff who are here. I want to say thank you to Michelle Rodriguez and Jen Tang for organizing this thing tonight, putting all the elements of it together. And as you're going to hear tonight, there's a really wonderful history here. And it really begins in 1869 with Mendeleev. Goes up through, well, you're going to hear. I don't want to give it away, but I do have to say, when I talk to other institutions, and we have a little natural competitive instinct here at Berkeley. I mean, when I go and talk to my others, nobody else can come even close to our 16 elements, and not to mention our 630 isotopes. So I'm really thrilled, and I want to introduce Paul Bartlett, who chairs our advisory board here, and and is also an emeritus professor of chemistry.
Thank you, Ken. It's my pleasure to speak on behalf of Rena Dorff, the director of... It's my pleasure to speak on behalf of Rena Dorff and the staff of the Lawrence Hall of Science and welcome you all this evening. Thanking you for your support as always. I also like to give a shout out to my chemistry colleague Lee Latimer, who is here helping to represent the American Chemical Society. Is this not working? Okay, well, all right. Look, I used to lecture in PSL, and I didn't have a microphone then. So can you hear me in the back if I don't use the mic at all? Yes. All right, here we go. So I think it's appropriate that we're celebrating the periodic table here at Berkeley and in an institution that's named in honor of Ernest O. Lawrence. The role that Lawrence played, the contributions which his team at the Berkeley Laboratory made, and the continuing impact of the Lawrence Berkeley National Laboratory in advancing science is something that will definitely play center stage tonight. But I'd like to tell you about some other aspects of the Lawrence Hall of Science, which are in quite a different direction. That is in advancing education. Now, I'm sure all of you are familiar with the public face of the Lawrence Hall of Science. The upper floors, the Public Science Center, teeming with enthusiastic school kids whenever the doors are open. Many of you probably had kids who had their first lab experience here, or perhaps participated in the summer camps that are run by the hall. But I think many of you are probably not familiar with everything that goes on behind the scenes here. The contributions which is being made by the hall staff in educational research, in developing training materials for teachers, and in developing teaching materials for students that are used in elementary and high schools across the world. To give you some perspective on this year there will be some 6,000 teachers who will receive training and materials to help them teach their science classes. And this year, more than 25% of the K-12 students across the United States will be using materials that were developed in this building. Pretty cool. Now, while these students and their teachers may not all make the connection between elements 97 and 103, as they're using their materials and getting excited about science, we can all take pride in the continuing contributions that are being made by Berkeley, by Lawrence, and by the institutions that bear these names. So with that, I'd like to turn the microphone over, even though I don't have it, turn it over to Mike Witherell, who is the current director of the Lawrence Berkeley National Laboratory.
Can you hear me? Great. So, I'm Mike Witherell. I'm thrilled to be the director of Brickley Lab and to be with you here tonight to speak a few minutes about Brickley Lab and the periodic table. So first, let me say a few words about Brickley Lab. This is a photo from 80 years ago, 1939. So this is the 60-inch cyclotron magnet yoke. This is E.O. Lawrence. He was 39 years old. That was the year he won his Nobel Prize for developing accelerator. This is his brother John, who was a medical researcher, was the first one to do medical use of accelerators. That's J. Robert Oppenheimer. He was a 38-year-old theoretical physicist at the time with the pipe before he went on to lead the Manhattan Project and found Los Alamos. That guy there, you might not know, that's Bob Wilson. He went on to build the biggest accelerators in the world at Fermi Lab. He was a 25-year-old graduate student that year. I was the 4th director at his lab, and I'm the 8th director at his lab, so I appreciate this picture. And that's Luis Alvarez, who was a 32-year-old physicist at the time. He went on to develop ground-based radar in the war for aviation, build the bubble chambers, won the Nobel Prize for that, and then went on and he and his son discovered what it was that ended the reign of the dinosaurs. So this was a pretty accomplished group. And our history comes out of that building of team science and great scientists. The one part we're trying not to reproduce, though, is that's the scientific staff, and to be clear about it, it's all white males, and that's something that, as you see, we're trying very much not to reproduce today. So, almost every field of science celebrates events in time when a fundamental part of the order of the universe was revealed to humans for the first time. For physicists, the first one was 1687 when Newton's Principia was published with the laws of motion and gravity. But there was a miracle decade in science from 1859 to 1869. For biologists, the publication of Darwin's On the Origin of Species was 1859, introduced the world to the meaning of mutation and variation and natural selection and evolution. The physicists, like myself, celebrate Maxwell's equations, which describe the electromagnetic field and how it relates to light in 4 equations. That was 1865. And then for chemists, the year to remember is 1869, when Mendeleev created the periodic table, exposing the way similar chemical properties repeat as the size of the atom increases. And of course, it was sometime later before people realized the cause of this. That is, the chemistry was determined by the number of electrons, and the number of electrons was determined by the number of protons in the nucleus. But the pattern was there. I recommend to all of you to listen to the Radio Lab podcast that Oliver Sacks talks about, the periodic table. He became obsessed with the periodic table as a young boy, and it got him through a very tough time in the war in London. And he goes on to narrate how Mendeleev made a deck of cards with one element on each card to think about them. And the story is that he actually had a dream where these things fell into a rows with the same characters, the same chemical, and that became the periodic table. Who knows, but it's a great story. So this is our part of the periodic table. We have 16 elements, about 12, 13%. As when somebody else comes and say, "Well, we have one called livermorium," I said, "Gee, that's great," But if I wore a button for every one of mine, I wouldn't have any, So, it's a marvelous thing, and it includes. And I'll talk a few about these, but. From 93 to 106, of course, that's from everything beyond uranium, 13 in a row, of course, was a miracle period for Berkeley. The first element we discovered was technetium. Of course, we historically, long before I was around, but there was a block in the periodic table that was empty in 1936. It had 34 known isotopes, but they were all unstable. And Emilio Segre, who was visiting Berkeley from Palermo, arranged to ship to Sicily a molybdenum strip that had been on a target at the accelerator here, targeted with deuterium, and he used that. Of course, he just sent it in the mail, which we wouldn't do these days. But discovered technetium, the first element to be discovered by synthesis. And they actually produced here first technetium 99M, which is an isotope which is now used in millions of diagnostic procedures every year. But then there's this 13 in a row beyond uranium, from Neptunium to seaborgium. And of course, in there are berkelium and californium and lawrencium. So from 40 to 74, Berkeley Lab scientists discovered all those. Glenn Seaborg led or co-led 8 of these teams. Alberto Giorso, 12 of them, which is a record. And I have one of the pictures I have in my office is this one. This actually, it has Darlene Hoffman, who worked here in on the chemistry of these and first discovered transuranic elements in natural rock and confirmed the discovery of seaborgium. She was the first woman to win the National Medal of Science for chemistry. So that was the beginning of a change in the demographic character of our scientific staff. And today, you'll hear a lot about this, but just let me pick out, take credit for a few. Rebecca Abergel leads a team that on the one hand discovers new ways to separate radioactive actinide elements from nuclear waste, and on the other hand, developed a compound to sequester actinides out of the body in case there's an event where we need that, where we need a pill that can do that for people. Now, my own research, well, this is a bit of what I was doing for research before I took this job, and I've now been cheerleading for it, is an experiment to look for dark matter in the laboratory, the Lex Zeppelin experiment, which uses 7 tons of liquid xenon in a highly instrumented tank 4,850 feet below the Black Mountains of South Dakota. And so my favorite element is xenon, because it's what we're using for that experiment. And we'll hear a little bit about that in a minute. But looking to the future, we're still building out our capability in chemistry of these heavy elements. So I'm pleased to announce that Polly Arnold, a fellow of the Royal Society and winner of the Rosalind Franklin Award, is going to be our new Director of Chemical Science Division. We were just able to announce this. So she's actually working on the bonding and reactivity of heavy elements, those blocks of the periodic table. And so this is still very much a live region of science. So now let me come back to one more thing, which is the other thing we're doing in our laboratory. We're having a very large program about inclusion, diversity, equity, and accountability, and celebrating the fact that fostering a diverse workforce in experience, perspective, and background, and a culture of inclusion are key to attracting and engaging the brightest minds and furthering our record of scientific excellence and groundbreaking innovation. It is the core of what we do. And we also celebrate institutions like the Lawrence Hall of Science that helps develop that diverse group of scientists for our future. So with that, I say thank you for being here on this warm night in Berkeley. What better to do on a warm night than to celebrate the periodic table? So thank you, and I'm now going to try to start an animation. Xenon's my favorite element because it's the perfect matter to look for dark matter. We are awash in dark matter. Most of the matter in the universe is dark, but we don't know what it is. The most important thing about finding dark matter is getting the quietest radioactive place you can imagine. So we go underground where the cosmic rays don't reach, and then we need to shield even from the rock around us, and the xenon's perfect for that. It is so dense that granite will float on it. Well, it turns out xenon is the air around us, but there's very, very little xenon. And so it takes a lot of work to actually get that, and it makes it pricey. We need 10 tons of xenon for this experiment, and that's about $10 million. The good news is when the experiment's all over, we get to sell it all back.
So good evening, everyone. And before I tell you who I am, I want to make sure that we're all in the right place, because maybe the heat got to some people's heads. So who here has heard of the periodic table before? Okay, so everyone is in the right place. Okay, so who has used the periodic table before? Okay, so we got a good crowd here. Okay, so final question. Who has used the periodic table to advance fundamental science and technology at Berkeley Lab before? Okay, so we have some volunteers to speak tonight. Great. Okay, excellent. Okay, so I'm just going to tell you now finally who I am. My name's Sinead Griffin, and I lead a group at Berkeley Lab's Molecular Foundry and Material Science Division. Sorry? It's on. You can't hear me, no, at the back? No? Okay, I'll use this one. Any better? Okay, we have action. Okay. So I lead a team in materials theory in the Material Science Division and the Molecular Foundry at the lab. And what we try to do is come up with creative and inventive ways of combining elements together to get new types of properties. So the types of problems that we're interested in range from coming up with the next combination of materials to replace silicon in your electronics, to coming up with new ideas for what the next type of quantum computer will be, so designing new types of quantum bits or qubits. And finally, one of the most interesting problems we're working on right now is what is the next generation of dark matter detector going to look like? So when Mike has sold all of his xenon back, what will the next detector look like? So as Mike kind of mentioned, the problem of finding dark matter is hard because dark matter doesn't interact with normal matter the way all of the elements in the periodic table do. This is because it doesn't interact with light the way we're used to thinking about seeing things. So in order to actually directly detect this, we need to come up with cunning schemes to try and directly find something that's invisible to normal materials. So that's all I'll tell you about dark matter for now, but maybe in 20 years' time we'll come back here to try and celebrate the dark periodic table. But for now, we'll just think of the periodic table that we know really well. So we heard some of the history of the periodic table already, and especially Berkeley Lab's pivotal role in founding 16 of these elements. So this all started back with Dmitry Mendeleev 150 years ago, who had this idea that maybe there was some structure to the physical and chemical properties that he could see. When he laid these all out, there were several gaps in what he saw as being the periodic table, which have been filled over the last 150 years. So I have here some of the pivotal characters and pivotal people that were involved in making the periodic table what it is today. So, of course, Marie Curie in the 1890s won not one, but 2 Nobel Prizes, both in chemistry and physics, for her work on radioactive elements. Then moving on to the 40s and 50s at Berkeley Lab, Glenn Seaborg, who we already heard about, was involved in 8 of the discoveries of elements. And right up to today, we have several groups, both in the US and internationally, trying to push forward the boundaries of what we know about the periodic table. One example of such a scientist is Dr. Clarice Phelps, who leads a team at Oak Ridge National Lab, one of our sister laboratories, who was involved in actually discovering tennessine, one of the more recently discovered elements. So that gives us, the 150 years of history, but we're interested in what we're going to be doing now. So what is contemporary research like in the periodic table, and what does the future of the periodic table look like? So that's what we've set for you today. We're going to hear from 5 of my colleagues at Berkeley Lab, 5 scientists who are doing some of the most interesting work in the world related to the periodic table. First off, we'll have Alan Poon, who will talk to us about how stardust can teach us about the history of the elements. Then we'll hear from Leanne Moreau, who will teach us about something that we probably saw in school, which was this big block of elements right at the end of the periodic table. And she'll be teaching us about what she's learning about those FBlock elements. Then we'll go on to Shwam Dwarkanath, who will teach us about how to make better batteries by bringing us on an elemental safari, and it's probably hot enough for that today. Then we'll go on to Laurie Steffi, who's trying to make supercomputers even more super by writing really smart algorithms to help in the search of dark energy. And finally, we'll hear from Jacqueline Gates, who will talk to us about how we're pushing forward the boundaries of the periodic table to try and discover new elements. Okay, so I'm sure you'll have lots and lots of questions, but we do have some ground rules. Since we're short on time tonight, we can't stay here all night. Please hold your questions until the end. We'll have a dedicated question and answer session right at the end of all of the speakers. Also, you'll probably want to learn lots more about the periodic table after tonight. And we have a dedicated website, which is Berkeley Lab, on the Berkeley Lab website, which is periodictable.lbl.gov. It has general history of the periodic table and some of the interesting information about the unique contributions of Berkeley Lab. We're also social at Berkeley Lab. We have a Twitter account at Berkeley Lab, which you can find about the day-to-day ongoing discoveries that happen at Berkeley Lab. And we also have 2 unique hashtags to celebrate Berkeley Lab's role in the periodic table, which are hashtag 16elements and hashtag myfavoriteelement. Finally, I'll be on Twitter live tweeting during the night, so if you have any questions and you're too shy to ask, feel free to tweet at me and we'll make sure to include them in the session. Okay, with that, I'd like to introduce the first speaker, Dr. Alan Poon.
Okay, I'm Alan Poon from Nuclear Science Division of Lawrence Berkeley Lab. First question. Do you know where did all the elements in the universe come from? Hands up if you know the answer. Okay, so I'm going to answer that question, I'm going to tell you the answer, but it's going to take a little bit of explanation. To answer that question, we have to go all the way back to the very early part of the universe, early beginning of the universe, okay? So within about a second after the universe was formed, okay, we start having protons and neutrons. You know what protons and neutrons are, right? And then within the first 3 minutes, we start having hydrogen, helium, and lithium, and then it stops there, okay, as the universe expands and cools down. This is where we are now, 13 billion years away from the beginning of the universe. But about a billion years after the start of the universe, of the Big Bang, structures start to form. So we have stars, we have galaxies, and in all these stellar objects is where a lot of the elements come from. So this is our sun. The surface is only about 1 million degrees in temperature. If you look at the core of the sun, it's tens of millions of degrees, and it's hot enough to start what we call a fusion process. In that case, this sun is full of hydrogen, protons and electrons, and the protons fuse together and form deuterium, and in the process, neutrinos, these are ghostly particles that are very hard to detect, are emitted. And then the process goes on. More protons are fused together, forming more objects. And then at the end of this, what we call PP chain, it forms helium. And this is how we get energy from the sun. Okay? What we're seeing on the surface are just the heat, but in the core of the sun, this is the fusion process that's happening. The takeaway is, in this process and the subsequent development of a lot of the elements, seeing the neutrinos is a key to establish that we have seen solar fusion. And to do that, we did one better than Mike. We went about a mile underground, turned a mine into a clean room. And we built a clean room, and here we, at Berkeley Lab, built this geodesic structure, and each one of these dots is a photomultiplier chip, it's a light sensor. And we fill this whole cavity with water, and inside this geodesic structure, we fill it with heavy water. And when neutrinos coming from the sun interacts with the heavy water inside the detector, it creates flashes of light. And then by measuring these flashes of light, we know we have seen neutrinos coming from the sun. And for that work, and the fact that we have that established in this experiment that neutrinos have mass, this experiment was awarded the Nobel Prize in 2015 in physics. So let's go back to the star. Okay, remember early in the universe, we go up to helium, and then we have protons fusing inside the sun. And for stars heavier than the sun, so we're burning hydrogen, and then over time, we'll start fusing helium. And then subsequently, we fuse carbon, neon, oxygen, silicon, but then over millions of years. Okay, but the time for each step gets shorter and shorter. And if the star is big enough, 10 times the mass of the sun, it will collapse into something called supernova. And we have seen a supernova back in 1987. And neutrino detectors on the ground have also seen the neutrinos coming from these supernova. And what's so special about these supernova? Because it's so dense that we can create all the elements, almost all the elements, up to uranium. This is what we see in everyday's world, in natural, these are the natural radioactivity that you see. My colleague, Jackie Gates, will tell you how she's going to make elements beyond uranium, from element 92 on, okay? But in the lab, we also try to figure out how nuclear reactions happen in the supernovae, because we want to see how all the elements are made. And we're building a detector called Greta. The gamma ray energy tracking array is being designed by Berkeley Lab. It has been approved by Department of Energy. And the idea is to build this detector, mount it as an accelerator facility where we can shoot radioactive beam inside this chamber where we have a target, and then we can measure the nuclear reaction, trying to understand the nuclear reaction and how supernovae create some of these elements. If this detector looks familiar, because you have seen it before. This is the Hawk, except that in this movie, the gamma sphere, which actually Berkeley Lab built, we built a gamma sphere back in the late 1990s and early 2000s. It was, in the movie, a gamma ray emitting device, but we're building a gamma ray detecting device. And now we have experience, so we're building a better one that will last more than one movie. So I'll stop here, and I will actually start a message from my boss of the division.
My favorite one has to be seaborgium. The biggest reason is because Professor Glenn Seaborg was my mentor when I was an undergrad here at Berkeley. After Seaborg had discovered so many elements, it was clear you had to name this one after him. So that was actually the first time an element was named after somebody who's alive. It's a very interesting element. It's very heavy. It doesn't hang around for very long. It decays. You can't find it in nature. These very heavy elements aren't used for any sort of application. The main reason we want to make them and study them is because they tell us actually how nuclei work. If you want to figure out how some stuff works, you kind of poke at it, you try and change it a little bit. So one of the things we do is we add extra neutrons. You add some extra protons, and that's when you start making these super heavy elements. And their structure changes. The big question that we want to answer is how do we use that understanding of the interaction of many particles together, many body physics, to do things that we can apply.
Do you remember sitting in chemistry class in high school and noticing those 2 rows on the periodic table that were slapped down at the bottom? Our teacher told us this was the FBlock, and then we never really talked about them again. Well, the reason is that these 2 rows don't really fit in with the rest of the periodic table. Mostly this is because of the way their outer electrons behave. These days, we have a pretty good idea of how the middle of the periodic table, that yellow portion, how their electrons behave. They like to move around a lot, kind of like a hyper-toddler. In contrast, the first of these 2 bottom F-block rows, which we refer to as the lanthanides after the first element in that row, lanthanum, has these super shielded outer electrons. Turns out the interactions with these different types of electrons in the lanthanides are quite useful and make them really reactive. Cerium, for example, you can find in your car's catalytic converter, helping make the gas emissions from your car much cleaner. Gadolinium is used to better image tumors or other internal organs as a contrast agent in MRI imaging. Praseodymium, neodymium, and europium are used in electronic applications, and more recently have found uses in screens to reduce glare. And then there's the bottom row of the FBlock, which we refer to as the actinides after first element actinium. These elements have a large number of electrons, and to be honest, we really don't have a good idea of how those electrons behave. In fact, most of these elements were only discovered post-1940, as was talked about earlier, right here at Berkeley Lab. And we're still one of the only places in the United States that has the facilities that are needed to study them. They behave in ways that are not predictable going across the periodic table. Uranium and the elements to the left of it occur naturally, and some are more common than you would think, while those to the right of uranium are made artificially. Uranium is about 40 times more abundant in Earth's crust than silver is, and there are about 1 million tons of thorium off the coast of India. One major use of the early actinides is for nuclear energy, which currently provides 20% of the United States' electrical energy. Some of the actinides, especially actinium, also show promise as potential agents for radiation-based medical therapies. Additionally, and this is one of my favorite parts of being a scientist, in studying materials properties, especially materials that we don't understand a lot about, often, as we come to understand them, new applications arise that we could not have previously anticipated. With such major applications, you can imagine the importance in understanding the lanthanides and actinides, especially as the problem gets even more complicated. It turns out that when we go ahead and make the FBlock materials really, really small, down to the nanometer length scale, they perform better. Now, for reference, a nanometer is about how long your fingernail just grew while I said that. When we make materials this small, we increase the percentage of atoms that are on the material's surface, so more of them are then available to react with what's around. This would mean more efficient catalytic converters and nuclear fuels. But we don't understand how these materials behave chemically on the nanoscale, and if we don't understand it, well, then we can't develop these materials for their applications. So that's where our team at the Berkeley Lab Heavy Element Chemistry Group comes in. We developed a new method to make and study nanoparticles that mimic small grains in lanthanide and actinide materials. Now here's how we do it. We incorporate a starting molecule into a porous template or mold. Imagine a really tiny sponge with nanometer-sized holes. Then we bake the molecules to form nanoparticles that are confined in their size by the pore size of our sponge-like template. By changing the size of the pores, we can control the size of the nanoparticles, and by changing the molecule we start with, we can explore a variety of potential elemental compositions. Think of it like changing the batter flavor when baking a cake. We know that our method is working because we have microscope images that show us nanoparticles that are confined in their size by our template pores. We have evidence to also confirm that the template material remains intact throughout the process. But to figure out how the nanoparticles are behaving differently from their larger bulk material counterparts, we really have to look at their structure on an even smaller length scale. So that's all the way down to the level of individual atoms. Now this is where advanced X-ray characterization tools come to our rescue by enabling us to probe the arrangements of individual atoms in the nanoparticles and compare them with bulk material. Interestingly, we do find that the nanoparticle structure is vastly different. For example, the nanoparticles are more disordered. Think a pile of bricks versus a brick wall. Different, right? Well, this would cause very different resulting properties. For example, in uranium oxide, we find that the response of our nanoparticles to a magnet is different than from the larger bulk material. More importantly, we find that the nanoparticle surface does not interact with the template, so the surface atoms are then still available to be involved in reactions. It's these differences in chemical structure that contribute to the differences that we see in performance in applications. Overall, we have successfully created a model system to look at properties of lanthanides and actinides and how they depend on their size. So far, we've already been making strides to expand across the periodic table in the FBlock elements. We have made nanoparticles of cerium, praseodymium, dysprosium, thorium, and uranium, and done some initial work with neptunium that looks very promising. We're excited to see how far we can go and how much more we can learn. We learned that with materials, bigger isn't always better, and you know, we're even learning that maybe the periodic table only gets better at the bottom. Oop. It seems to not.
Right now, I'm very motivated by actinium-225. It looks to be an extremely promising candidate for the treatment of cancer, and it's extremely hard to make. And we are exploring alternative production pathways for it. Actinium-225 has a half-life of 9.9 days. So we can make it, and it will hang out long enough that it can be connected to a specific chemical in a process called labeling. Then that chemical can be injected into people, and it will seek out particular cancer locations. And when it undergoes its radioactive decay, because it is unstable with a 9.9-day lifetime, it will release energy that's very local. It will damage the cancer cell, and in particular do a very important kind of damage called double-strand DNA damage. And in the neat case of actinium, it will then go through a series of very quick decays and be completely done in about 3 hours. Right now, I'm very motivated by actinium.
Oh, there we go. So I'm Sham Dwarknath. I'm a research scientist at LBL, and I'm going to talk to you about designing better batteries with the Elemental Safari. So some of our most pressing challenges today revolve around our use of the periodic table. Really, it's our very selective use of the periodic table. As we move away from a carbon-based economy, based on burning fossil fuels, based on converting petroleum into plastics, and really based on using things or disposing of things that should be reusable, we need to make sure we don't recreate these problems. In today's world, we're moving towards electric vehicles, but the batteries that we use to build these vehicles are made from the periodic table. So we need to look at it more closely to understand where these problems arise. If we think about this very closely, we know that there's lithium in batteries. It's only one below hydrogen, right? But what else is there? Well, there's iron and nickel, cobalt and manganese, carbon and nitrogen, oxygen and fluorine. But these aren't just Lego blocks, right? They are not just inanimate objects that have no other character. They actually have quite a bit of personality that gives them very unique properties and very unique behavior. So if we want to think about this a little bit more closely, we can think of lithium like a sparrow. It's flying high above the safari, doesn't have a care in the world, but eventually it gets tired and it has to land somewhere. There's no trees in sight. So what does it do? It lands on an elephant. It's big, it's slow, it's moving very slowly, and it doesn't really care the sparrow's there, right? Just like cobalt in our batteries. This is what lets our batteries become rechargeable, because the lithium can come to the cobalt the same way the sparrow comes to the elephant, and it doesn't bother it. But, cobalt is not something that's very easy to get. It's actually rather hard. And just like the elephants that are there, it actually eventually figures out the lithium's there. It'll try to swat it away with its ears, and eventually the cobalt, or the elephant, actually passes away. So our batteries fail at some point. Now, like big elephants, it turns out cobalt's actually harder and harder to find today. In fact, it's more than half of the cobalt in the world today is produced in a country in Africa called the Democratic Republic of Congo. Now, this country has lots of political and economic problems. As a result of that, cobalt ends up being a conflict mineral. Think conflict diamonds, right? So children are actually mining cobalt in very harsh conditions. So we want to move away from cobalt and make our batteries out of something very different. So we have to go back to the periodic table. So let's look at this a little more closely and think about what's there. Well, there's iron and nickel, there's manganese and copper, there's zinc and chromium, okay? But as I mentioned before, these aren't just inanimate objects, they have character. Unfortunately, they're not as nice as cobalt. If we look at nickel and copper, we can think of them like big cats, right? They hide in the safari pretty well, and if you're that sparrow, you probably don't want to land on them because they might eat you. Manganese and iron, we can think of them like rhinos and buffalo. Yeah, they're big, but as soon as you land on it, it's going to shoo you away. So it's going to be really hard to just come and go. Chrome and zinc, we can think of like antelope and zebra. They're really, really fast, so you have to catch it to land, and that's going to take a lot of effort. All of what this does is it makes it really hard for the sparrow to land within this pack of animals. And the analogy is that it's very hard to build a battery with any one of these elements and have it work with lithium. But maybe there's a different solution. Let's change from lithium. What else is there? Well, there's sodium, there's potassium, there's magnesium and calcium. These have a double charge, so maybe we can make batteries that are twice as good. But it turns out there's another set of problems here. Yeah, we can make batteries with these elements, but just like storks and toucans and ostrich and penguin, which are all technically birds, they all have a very different environment. They have a different watering hole, and they have a different set of animals that are there that let them come and go as they want to. So if we really want to build better batteries, we have to design the right set of elements. So at LBL, what we're doing is we're trying to figure out how do you put the right set of elements together that work in harmony in such a way so that you can support lithium, sodium, potassium, or even potentially magnesium or chromium batteries to really solve some of our key energy challenges. What we're really doing is trying to make that perfect watering hole for these elements. Thank you.
My favorite element is carbon. Our bodies are made of carbon and water. The foods we eat are made of carbon. The fuels that we burn for transportation are made of carbon. The reason it's my favorite element is because it's the one that taught me how to be a chemist. When I started college, I started as a chemistry major because that's what pre-meds did. And so I took all the normal chemistry curriculum, and it basically didn't go very well. I found I had to memorize everything. I didn't understand anything of what they were teaching me. So at the end of the year, I thought, okay, I've had great classes in English. I'm going to be an English major, and I'm just going to go ahead and do one more year of chemistry, so at least I have the minor in it. And so that meant I signed up for organic chemistry in my sophomore year. And I loved it. All of a sudden, everything began to make sense because carbon has a very simple electronic structure. It forms very specific types of bonds, and the rules of how it reacts with itself and with other elements are actually pretty straightforward to understand. All of the diversity of chemistry that we have around us, the way our bodies work, the way the world works, which is all based on carbon, is all governed by a very small number of rules of how chemistry actually works. And once I understood that, it was like, of course, this all makes sense. You know, this is rational. And I just went from there. My favorite.
Sorry. See if I can get this right. Hi, everyone. My name is Lori Steffi. I work at NERSC, which is the National Energy Research Scientific Computing Center. We're in Building 59, right down the hill at LBL. That's the top picture. And I'm going to tell you about how we have made DESI's software. DESI is a dark energy experiment. I'll get to that in a second. How we've improved how their software runs on our supercomputers. And the bottom picture is Cori. This is our current fastest supercomputer. All of our systems are named for scientists. So this one is named for Gertie Cori, the first American woman to win the Nobel Prize. Are any of you scientists? Yeah? So maybe one day our next system will be named after one of you. All right, so let's remember a time only 80 short years ago that computers were the size of a building and they were full of vacuum tubes. So ENIAC was our first general purpose electronic computer, and it had 20,000 vacuum tubes, like light bulbs. And ENIAC could do a very speedy 500 floating point operations per second, we call flops. And that seems like quite a bit. That's way more than I can do. But if you compare that to Cori, which I just showed, which can do almost 3 petaflops, that's 10 to the 15, or 3 million billion floating point operations per second, it's clear how far we have come in just 80 short years. I think it's pretty incredible. So you might be wondering, how did we go from vacuum tubes to what we have now? And the answer is silicon. So we're here celebrating the periodic table, and silicon has been key to the computing revolution that we've all been fortunate to experience. So one of the very first example, or the first computer to use integrated circuits was the Apollo guidance computer. And of course, launching ENIAC into space would be completely absurd, but NASA needed a computer to help calculate the trajectories to get astronauts to and from the moon. And so they really pushed on the development of small, but still powerful computers, and that's how we've come to the silicon-based semiconductor technology that we like today. So silicon is a semiconductor, which means sometimes conducting, sometimes not. And if you add materials called dopants, which in this case are P and N, you put them together, and now you have a one-way gate. So electrons can go through one way, but not the other. And that's really powerful, because when you have that, you can build up logic. And when you have many logic units, now you have integrated circuits. And when you have that, you have computers. So yeah, this was 50 years ago, very, very closely, now that we just had our first integrated circuit computer. And of course, technology continues to improve. Chips get smaller, they get faster, they're everywhere. They're in our watches and our phones and our refrigerators. So this has been really powerful. Okay, but we still need big computers to answer some of our biggest questions. And one question is, what is dark energy? So does anybody know what dark energy is? Trick question. Nobody knows what dark energy is. So right now, we estimate that it's almost 70% of our universe, but we really don't have a good understanding of its physics. We can't really write down any equations that describe it. So the DESI experiment, which is also based down the hill at LBL, is trying to help understand what is dark energy. So it stands for the Dark Energy Spectroscopic Instrument. It's being installed right now in Kitt Peak, Arizona, and they're going to start taking data this fall, which is exciting. DESI, over the course of 5 years, is going to make the largest, most detailed 3D map of the universe ever. And when we have that, then we can sort of get a better idea of how dark energy has influenced the universe. So that's really cool. Logistically, how do you do that? You take data every night for 5 years, and you ship it to us. We're going to help process the data, get it back to them, so they can decide, was this good? Was this bad? Can we point this telescope somewhere else? So as soon as they get this information, the time is valuable for them because they're getting ready for their next night. So of course, nobody wants slow software. They want to have their answer as quickly as possible. So that's where we have helped them. We have taken a look at their software, and like any good scientist, we have taken data to figure out where it was slow. And once we found the bottlenecks, so think of it like a traffic jam, we have adjusted their software to alleviate these traffic problems. So that means we have restructured their software to avoid expensive parts, or because it's in Python, we do something called just-in-time compiling, which makes it super fast. So we have done this, and now their code is 7 times faster. So that's really great for them. That means they get their science results faster, and they can make better plans. That's also good because we are trying to use less energy. Supercomputers are very energy hungry. Cori is using maybe 4 megawatts, which is a lot. So anything we can do to cut down on that really adds up. It also means less carbon is emitted in the process. The other thing is supercomputers are big and expensive, and everybody wants to use them. People wait in line because they're just oversubscribed. So the sooner we can get DESI's calculation done and moved on, one of our other 7,000 scientists that's been waiting in line can now have access and get their own work done too. So who doesn't like getting 7 times as much work done in the same amount of time? Thank you.
Carbon's my favorite element because it makes a lot of things. It's in food, it's in pencils, it's in diamonds.
Titanium is like lightweight and it's really like hard and like hard to destruct, so I kind of like that.
Element? What's an element? It is mercury because mercury is a liquid at room temperature, and when it heats up, the mercury expands, and that's how thermometers are used.
I chose cadmium because it's used in paints, and I really like to do art and painting.
Fluoride, so then it just keeps your teeth healthy, so then you can chew and eat easier. They won't fall out like, you know who, back in time.
Oh no.
Carbon's my favorite element because it makes a lot of
Hi, my name is Jacqueline Gates, and what I want to talk to you today is Alchemy, because I have the pleasure of running one of the Alchemy groups at Berkeley Lab. Now, when you think about alchemy, this is what I think about. I think about some scientist locked away in a tower in some old castle, slinging over a bunch of beakers, giving off noxious fumes, trying to find a way to transform lead into gold. Now, back in the medieval ages and the ancient times, they never succeeded. But today, this is something that we can do and something that we do at labs all around the world. In fact, we do this at Berkeley, right down the hill. The reason why we have succeeded and they have failed is because we understand a little bit more about the elements than they did. In fact, we know that elements these days are collections of protons and neutrons inside of a nucleus surrounded by an electron cloud. And so if you want to make one atom into another or one element into another, the way you have to do it is by adding 2 elements together. You have to take the nuclei of one atom, add it to the nucleus of another, and then you get some sort of new element. Now, unfortunately, this isn't a very easy process. Nuclei, atoms are incredibly tiny. There's about, I think it's about 5 sextillion atoms in a drop of water. So they're very small. And nuclei inside of an atom are even smaller. If an atom is the size of this room, the nucleus is about the size of a period on a piece of paper. And my job is to find 2 of those nuclei and combine them together. And so the way that we do it is just by a very simple 5-step process. It actually is very simple in theory. We take one atom and we shoot it at a bunch of others. And we hope that the nuclei combine. And we hope that they make what we want. And that's kind of like step 3. We have to be lucky and get what we want. And then we have to take that one atom that we made and separate it out from everything that we didn't make. So we have to separate out from everything that we fired at the other atoms. We have to separate it out from targets. And then we have to detect it. And we've actually been very successful at that. So this is a periodic table, which you have seen many times before. As it's been mentioned, most of the elements up to uranium are naturally occurring. But there's 26 elements, well, 24 heavier than uranium, and 2 that are lighter, that are not found naturally here on Earth. Berkeley Lab, as you've already heard, was the discoverer of 16 of these elements. My group, what we study are the heaviest elements. We study things called super heavy elements. And there's a couple of things to know about these guys. First of all, when we make them one single atom at a time. And we don't make them very easily either. With our best accelerators and our best technology, we can make maybe an atom a second if it's Rutherfordium, element 104 there. And if we're trying to go for oganesson, which is the heaviest known element, we can make maybe an atom a week. And so one of the questions is, why would we bother doing this? Why would we study something that, you have a single atom every second or maybe an atom every week? And there's a couple of reasons. One is the search for knowledge and the search for fundamental science. Can we understand how elements are created? Because that might help us understand how the elements that form us and form our universe are created in stars. One thing is, maybe these elements have interesting properties that we don't know about that can lead to useful uses. For instance, if you go back to the elements that Berkeley discovered, plutonium was first discovered in 1940, and it was discovered with these same processes, making a single atom of plutonium at a time. Well, now we make plutonium and we use it in nuclear reactors to power our cities. Americium, again, it was made a single atom at a time. Well, now it's in most of the smoke detectors in your houses, keeping you safe. Curium is used to look for oil and gas reserves. A lot of these elements are also used in medical researches to do radiation therapy, cancer treatments, and that sort of thing. And so maybe these heavier guys could be used as well. And the reason why we think that might be the case is this chart here. So when a physicist thinks of the periodic table, this is what they think about. Instead of having your elements increase as you go across the thing, elements increase as you go up. And that spit of land are the isotopes that we know. So combinations of protons and neutrons that we know exist on this Earth. Where there are mountains or ridges, those are incredibly stable elements. So the ones that you're most likely to be able to dig out of the ground. Magic Ridge up there, that's things around lead. The end of the Actinide Peninsula, that's uranium. Magic Island out there, that's somewhere around element 118, the element that we have recently discovered and added to the periodic table just 2 years ago. And things around Magic Island are predicted to have lifetimes of years, maybe centuries, depending on the theory, or even longer. It could be that eventually we come up with ways to make these elements in large quantities, and we can come up with useful applications for them. And I was the last speaker.
Did you all enjoy that? Yeah? So while I invite our 5 staff scientists back to the stage, can we give one more round of applause to the 5 scientists? So the way this is going to work is that we have 2 microphones. So if you'd like to ask a question, please put up your hand and wave it so that we can see you. And give us a minute till someone runs up to you and gives a mic to you. Okay, so first question.
This is for Jacqueline. Do any of these heavy elements form in great big stars?
Maybe. The answer is we don't know, because we actually don't know very well how the heaviest elements are formed in stars. So we know uranium clearly is formed in stars. Plutonium was discovered here on Earth as well, so that's clearly formed. You would think that the heavier things are also formed and that they've just decayed away since the Earth is 4.5 billion years old, and these have lifetimes on the order of thousands of years.
Hi, real quick, any relativistic effects from the mass of the nucleus on the electrons in the orbit of the very heaviest elements?
Yes, so I didn't speak about that, but you are correct. As you go to, well, relativistic effects essentially are, as you add more and more protons into the system, those protons kind of, this is a very basic physicist understanding of it, those protons kind of attract the electrons a little bit more, the inner electrons. And those inner electrons then shield the outer electrons. And so what you get is a contraction of some electrons and an expansion of others. And this can change your chemistry. As you go up in Z, so as you go up in proton number, these relativistic effects increase by the square of the proton number. And so when you get up to the very, very heavy things, you no longer expect chemistry to behave the way it does in lighter atoms. So you could expect that flerovium, which is underneath lead in the periodic table, am I right? Okay. Maybe it doesn't behave like lead. Maybe it behaves more like mercury, or even more like radon. And if we can understand how these relativistic effects impact the heavy ions, that can actually help us understand relativistic effects in the lighter ions. Because if you think about gold, it's gold, whereas everything else around it is silver and colored. And the reason gold is due to how the nucleus impacts the electrons and how that changes the chemistry. And the same thing with mercury. It's a liquid, whereas everything else around it is solid. And it's liquid due to the impact of this positive charge in the nucleus on the electrons around it, changing the chemistry of the atom.
This question is for anybody that can answer it. I've always been intrigued why so many of the elements are so inhomogeneously distributed in the Earth. So why did the cobalt all end up, or a big mass of it, in the Congo, of all places? Why isn't it?
Okay. So I'm not a geologist, but from what I understand, it's not so much that it's all in the Congo, it's just that's where it's easy for us to access it. It's actually kind of distributed in the Earth's crust overall, and there are pockets of mines that happen to have easy access to it. So we could find it maybe in somewhere else, we just haven't found the correct mine. Where is the microphone?
Exercise tonight.
Is lithium used in our best battery so far because it's the smallest metallic element, so you can pack more of them into a container so you can get a heavier charge? And why not compound it with chloride, so you have lithium chloride? Is that a good compound?
So lithium is used because it is very small, and so it's very easy to put into your battery and pull it back out. It's not about how much charge is there, it's about how easy it is to put it in and take it out, right? Think of like having two magnets, and if you have really strong magnets, it's really hard to pull them apart. If you have two weak magnets, it's kind of easy to pull it apart. That's effectively what lithium gives us. It's very easy to do that. And it's the same reason why you wouldn't have lithium chloride. It's very hard to separate those two if you have them, and so you have to do a lot of work in order to get this energy versus I can very easily put it in my battery and take it back out of the battery.
Oh.
Where's the microphone?
Hi. So what, if any, significance is there to the colors that are used in a chart to depict the various elements?
Want to use?
I've seen charts with different colors. If you go to Wikipedia, as I did this morning, doing final prep for this event, there are charts that tell you where some of the elements are made, what type of stars that it is made in. But in general, the periodic table, you look at the families, the columns, and then it actually tells you the electronic structure of the different elements. Yeah. But color, I'm not so sure.
Well, I do have a chemistry degree. I just haven't used it in a decade, so let me have this one. The color is usually the type of element it is. So if it's a rare gas, it's going to be one color. If it's an alkali metal, it's going to be a different color. If it's a transition metal, it'll be a different. So it tells you a little bit about the chemistry and how that is compared to the elements around it.
I want to ask this, Xiam. It was very interesting that you described the battery elements as animals, but I want to know about your opinion about the oxygen and fluoride, which is an ion.
I couldn't figure out the right animals for those because those are always there and you need them. Maybe they're more like the water in the watering hole or the trees that are there, so maybe that's the better analogy for those.
I have a non-scientific question. It struck me in the presentations that all of the younger ones spoke very clearly and beautifully and managed the instrumentation well. But all the older members seemed to have great trouble avoiding dropping their voice at the end of a sentence, didn't know how to handle a microphone. So it seems to me the modern generation's really learned something that the older one hasn't grasped yet.
I'm going to give that to Mike. I think Mike can answer that one. Well, we can hear you, but she's coming.
Sorry, I'm trying to look out.
Thanks. I noticed the organesson finally fills out the actinide sequence. When's somebody going to discover 119, and where the hell will it go on the periodic table?
So there are attempts to discover element 119 ongoing currently. There have been attempts at GSI, which is a laboratory in Germany, to discover 119, to try and look for 120 and 124, I believe. Those were unsuccessful. There were experiments in Dubna, Russia, also attempting to discover, I think, 120. But right now there is an ongoing experiment in Riken in Japan. And they should discover 119 within the next year or two, would be my guess. Where it will go on the chart, it'll be the S block. Are we on 8S or 9S?
Hi, I have a question on behalf of this guy here who you might notice is wearing a Tennessee shirt. He was too shy. He was too shy to ask. But what kind of education does one need to join a group that's studying elements and discovering new elements? That's really one of his career goals.
So I and almost everyone in my group have doctorates in either nuclear chemistry or nuclear physics. And if you're going to be in one of the heavy element groups, there's only a couple in the US, and that's pretty much the requirement to be a full-time member in the group, is a doctorate in nuclear chemistry or nuclear physics.
That being said, one of the really awesome things about working up through an education is even if you got your doctorate in like nuclear physics or nuclear chemistry, one can also get other degrees before that that can kind of morph into that. For example, I was a material science engineer in my undergraduate, well, and PhD, but the work I'm doing now is more chemistry focused. So you can also kind of consider that we're reaching the point where all the fields of science are kind of needing to branch together. And so once you find what you're interested in, that might, kind of also evolve into still reaching the same career goal, but taking a different path.
I had a question about using radioactive chemicals for cancer treatment. In terms of injection, how does it find the cancer cells? And then after it's treated the cancer cells, what does it break down to? Like what molecules do the radioactive chemicals break down to, and how does it leave the body?
Well, so from what I understand, typically it would not just simply be injecting an isotope by itself. It would typically be bound to some sort of antibody, which would then have recognition for the cancer cell specifically if it's designed such to do that. And then depending on what type of isotope is used, that will determine what it breaks down into. That's one of the reasons why actinium is one of the ones that they're looking into, is because it decays very quickly and in such a way that it will decay and create its nuclear products without really causing too much damage at the end. Anyone else have any thoughts?
What is the reason that the lab stopped discovering new heavy elements after 106?
Yeah, pretty much what Mike said. It got harder. So You can discover elements up to 106 by just needing a particle accelerator and some good chemists. To go up to 107, you can't use chemistry anymore to separate out your single atom from all the junk because the stuff doesn't last long enough. Then you need a physical pre-separator. And while we have one now at Berkeley, we didn't have one until after most of those elements were discovered.
I was curious, isn't it possible for us to produce cobalt in huge quantities so that we don't have to mine it in the Congo?
So, how would I answer this question? I could ask Jackie to make it, but apparently it would cost way too much. So most of the, I was going to say most of the elements below uranium occur naturally, and they come through natural processes, either from the sun or supernovae. So it's much easier for us to basically mine it out of the earth, right? This is relatively safe and easy, and you don't need Berkeley Lab in order to mine something like that. I would say the next best step for us is really to find something other than cobalt, because there are so many other elements on the periodic table. The problem is that there are so many elements on the periodic table, and there's only so few scientists who can go ahead and try all these different combinations. And that's why we need people like you and other people, and our future scientists, to continue to be curious and develop the degrees in math and science, even in like English and communication, so that we can continue this process of building the next generation of curious minds that will solve very, very difficult challenges, such as what are all of our energy problems today.
So yeah, my question up here is like, so right now, like the elements that have been discovered are up to 118. So is there like a theoretical limit to just how high like an atomic number could go, but like to a point where it's like it just can't be, it's not stable for like any time at all?
It depends on what theoretician you ask. So element 172 is a number that's thrown about because I think the reason that they say is that once you get up to 172 protons, the inner electrons are pulled so close into the nucleus that they're actually at a negative energy. And you can't have things at a negative energy. There are other theoreticians who say, well, we just don't understand science that well at that level, and there could be something else going on that we haven't even thought about. So maybe you can go up to element 300. Who knows?
Yes, this question was about the nanoparticles, and you were putting the nanoparticles in like a matrix so you could get different sizes of nanoparticles. What is the matrix made of? What elements?
So it's a material called a covalent organic framework. It's mostly made of carbon, so it's inorganic material, carbon, boron, oxygen, and nitrogen. So those are the majority of the material in that. But you can imagine using a variety of different types of templates, and that's something that we've thought of playing with, something like a porous silica, which would be like a glass template, or something of that nature. So really it's functioning as a template and not the material itself. But we like the one that we use is because it doesn't have a lot of really reactive elements, and so it doesn't really react with the particles itself to make them fall apart or that the template falls apart.
If a nucleus is so small compared to the atom, what's the rest of the atom?
Empty space. It's just nothing, which is actually a really cool concept if you think about it, because you and I and everything around us is mostly nothing.
Moving fast.
Well, you have electrons, but electrons are really tiny, and so most of your atom is empty space.
So when you isolate these teeny tiny things, where do you put them and how do you see them?
We put them into silicon. Because silicon has because everything that we make, at least now, it decays pretty fast. And when it decays, it gives off energy. If we put it into silicon, we can record that energy. And the type of energy it gives off is characteristic to what we have made. And so by measuring this energy, we can figure out what we made. And we can figure out really interesting things about it, like what's the shape of its nucleus. We can even figure out a little bit about its chemistry just by looking at this type of thing.
I wasn't sure I heard this correctly. There was a brief reference at the beginning about extracting radioactive material from the human body. And I'm wondering if anybody can comment on that.
About naturally occurring ones?
No, somebody who's been contaminated.
Okay, right. So there are, obviously, if there were any sort of like radioactive contamination of having heavy elements that would, for some reason, get into the body, it's important to have ways to take that out. And so one thing that the Abergel group, which is a group in the heavy element chemistry group in the lab, is doing is they came up with particular types of molecules that bind really, really strongly to those types of heavy elements. And then by doing that, they can be cleared once they're in that encapsulated form from the body. And it turns out these molecules are really, really efficient at doing just that and being able to separate out those types of atoms from the other types. I'm not sure too many details of the clearance mechanism, but my thought is that because these molecules are pretty big that are encapsulating and binding really tightly, that the body would treat it more as the molecule than it would as the ion itself.
Hi, so I was noticing you were talking about how the heavy metal, like the lanthanides, actinides, would react with stuff in the body, and I was wondering if there were any other cool organic chemistry applications or like organoactinide with like, you know how barium is used to X-ray, like barium meals are eaten and they're X-rayed through the body. Are there any other applications like that with the heavy and actinide elements?
Well, I mean, so one thing that I had mentioned was using gadolinium for MRI imaging. Basically, because it's so heavy, it has a greater contrast in that sort of imaging. And so as a result of that, it can be used as a tracer to be collected at particular sites for that imaging. So that would be one sort of type. I mean, the reality is that we're still trying to understand a lot of the organic chemistry around the actinides. I mean, there are potential uses for catalytic applications, and so making reactions faster. But part of the problem is the lanthanides are also pretty good for that, and a lot of other types of elements that then don't have the radioactivity issues. And so typically, we would not consider using those types of elements for those applications, but who knows, maybe one day we'll find a particular reaction for which those work a lot better.
I have a simple question. When we are talking about the history of periodic table, I wonder if the speed of the computation nowadays with the analysis and all, has it sped up the discovery of new elements in the periodic table? Has it sped up all the information that's flowing out?
I'm not an expert on this, but I know that there's a lot of materials discovery simulations that people are doing on our systems and trying out not just elements, but molecules, structures, all kinds of things. I don't know if someone else has.
So I would say computation in general is really having a huge effect on science across the board. Whether it's new materials, it's new biology, it's understanding medicine better, it's understanding our climate. The ability to simulate very large things is really a new capability that we're just starting to really understand, not only in terms of the science that's involved, but how do we use it effectively to impact change in terms of our policy and our future. So this is definitely the next frontier for science, and Berkeley Lab is one of the pioneers in this space, by not only including the computation, but including everything else around that, from the people doing the domain science to experts on policy and how do you effectively get climate policy in countries across the country or across the world that is effective for that local region versus just the United States.
So I've got a question about like elements heavier than uranium are potentially produced in a supernova. Could we look into the gamma spectrum in the supernova, like below that it may emit gamma. So could we look at those specific lines to see, do we find line that we can't recognize from all our long isotope, and does it correspond to a specific?
So for example, for uranium, the half-life is 10 to the 9 years or so. The problem is for some of these super heavy elements, their half-life is very, very short. So it's really difficult to see them. Remember that even if they travel at the speed of light, by the time that they go from there to us, it's a long time.
Dark matter. Say we did put together or collect dark matter, what would we do with it? What would we use it for?
So you might be able to have more ideas than we do right now. So we don't know what dark matter is yet. We know it's there because we've lots of different types of observations that it's there, but we don't know anything about it. So we aren't even at the stage of building up a periodic table of dark matter because we don't know its properties. So maybe when you're a scientist, you can help us find out what it would be useful for.
Thank you.
Sorry, I'm going to talk since I've got the microphone. I'm looking at the time. I think we have time for one more question, and then we'll get you out of here since it's almost 8:30. I'm going to run up there.
Hi there. First of all, thanks a lot for this program. It's really a great knowledge source, and thanks a lot for all your time and meaningful contributions to science. My question is more towards the software. We live in Silicon Valley, and we know the value of open source software. And it's really great to see Berkeley Lab's contribution and like 16 or like similar number of elements. And it was great to know that how hard it has become to crunch newer elements wherever we are. What is Berkeley Lab doing to expand its knowledge source and spread it? Let's say that it's really hard, the nuclear, the setup, right? To shoot the subatomic particles or whatever, but once you get whatever small data you have, what is Berkeley Lab doing to spread that knowledge or spread that data set so that it's available to the rest of the world to really crunch their minds and do their own magic on that data set?
Well, so this is not necessarily about the new elements, but Berkeley is the home for really a lot of the open source kind of projects that have produced the internet, right? The Berkeley software distribution comes from here. And so, we have this ethos of taking or finding new information and then spreading it around the world so that everyone can benefit from this. And LBL specifically is doing a number of projects that are pioneering data for a variety of science domains. I come from a project where we're trying to have an open database of materials properties, effectively a Google for materials. So when you want to go find your new battery, you can effectively just search and say, I want a battery that will do this, this, and this. Or I want the next solar photovoltaic material that's going to give me the best efficiency on my car. Or I want the next motor material, or whatever it is. This is really a fundamental challenge for us moving forward, and we're trying to develop the capabilities so that anyone can develop materials for whichever application they're trying to solve.
Okay, I think we have to call it a night. But first off, thanks to all our scientists for spending their evening here. We also want to thank Berkeley Lab and the Lawrence Hall of Science as well for hosting this evening. And finally, thank you all for coming and for asking such great questions. We'll see you next time.